Hey friends, welcome back. Our next lesson is called Counting All Functions. And I love this lesson because it relates and connects together two probably seemingly disconnected areas in math that we've studied in the past. And one of them is what we have been studying with counting. So our mindset message because of that is find the beauty in math. For me, math is so beautiful because of how interconnected it is. Our main one learning goal for today is to connect counting problems to functions. And those are those two topics I was saying we're going to kind of meld together and relate. Prior knowledge then would be our counting techniques we've been developing recently. And then remembering what functions are. So the definition of functions and remembering what domain and range are. So let's dive into an example to kind of see how these relate. So here's a recent problem that you might be familiar with. Suppose you flip a coin 3 times and record the outcome. How many possible outcomes are there? And remember, an outcome in this case would be like 3 coins. So heads, tails, tails. That's one outcome, right? So we've talked about similar problems there. But how does this relate to functions? And how can this actually help us answer this question? So if we want to think of this involving functions, let's go back to something important. Remember that a function, really all it is taking one set and another set and pairing the elements in the sets together. Now really what we need to do is make sure all the domain, remember that's like our inputs, everything in the domain is going to have a match. Not everything here has to be matched to, and this should make sense to you because I could have 1, 2, and 3. All those tosses could be tails, for example, right? And that would represent one particular function. So if each of these all ended up as tails, that's one function because that's one relation between these elements in the domain and some of the elements in the range, okay? So in our particular case, the toss number, right, is going to form our domain, and then the possible outcomes is going to be our range. Now, it's important to remember, in counting problems, when we're thinking about counting all the functions up, always the domain is going to be like a way to label the slots you're filling. If we think of the pathway method that we've learned to count things. So if I think of this as like toss 1, 2, and 3, and this could be a head or a tails, but so could this or this. So each one of these has 2 possibilities it could form, and so we have a total of 8 different outcomes possible. What this means is there are 8 different functions we could form from the elements here and the elements there by matching them up based on what a function is. Let's take a look at another example that is fundamentally different from these functions here. So here we have a class of 9 students and they're trying to play Foursquare. How many ways are there to choose 4 of them to play this game? Now of course, if you're familiar with Foursquare, you can kind of change in, but let's just say to start the game out, you've got to choose 4 people. And just to remind you, Foursquare consists of 4 squares, and there are 4 different people that you'd place in those squares, right? And one of the fundamental differences between this and the last problem was that if you're placing people into these squares, you can't put the same person into 2 different squares. In the last one, 2 different spots could be tails, and that'd be fine, right? But in this case, that's not true. So let's relate this to functions and talk about how all these functions are different from the functions based on the last problem. So again, we're going to set up one of these mapping diagrams, we call them, and label the domain and range. Think for me real quick, or think for yourself, what in this case would be the domain? Well, the domain would essentially be the square number that somebody's standing in. So it could be 1, 2, 3, or 4. And the range would happen to be the person or the people that get matched to the square number. Let's say 4 of the people's names are Kiet, Isabel, Sophia, and Ethan out of this class of 9. So one way to assign it would be, this person's in 4, this person's in 3, that person's in number 2, and that person's in number 1. This is one function which represents one possible outcome of the situation. But how do we actually calculate this? This helps us understand conceptually about how functions are connected to this. But how do we do the calculation? Let's look at that. So again, we have slots to fill, right? And in this case, let's just say square 1 in the 4 square. How many people exist that we could put into square 1? Well, we have 9 students, right? So 9 possibilities there. And this is where this fundamental difference between these functions and the ones in the last problem come into play. Once a person's been used in this slot, they can't be used again, right? So there would be 8 people then available for square 2, let's say, 7 people available for the next one, and then 6 to choose from for the next one. And if we actually multiplied that all together, it'll give us the total number of ways we could choose 4 people out of this class to start out our 4 square game, which would be 3,024. In fact, actually, yes, I'm correct. I thought I was incorrect. Okay, so here's in function terminology, bringing back some old vocab from a past course. Here's the difference between this kind of function and the last one. Each of the functions related to this problem here is what we call one-to-one. And that's an easy one to remember, because what we mean is one thing from the domain matches with exactly one thing from the range, and then that's it, right? Kiet could not stand in 2 squares at once, right? So every person in my group of 4 ends up being assigned only to one thing. So all the functions involved here are one-to-one. And you can go back if you want and label the last one. Those functions are just regular old functions that are not one-to-one, because you could get a heads or tails more than once in any of the slots as we flip the coins, right? Because it's not dependent on previous outcomes. So that forms a core foundation for something we're going to jump into as we move forward in this course, is relating these to functions. So let's go over a couple other counting problems with functions to end off. Okay, let's look at 2 different sets of numbers here, and we are asking to consider the possible functions from this set to this set. Now, when I use that language, what I mean is we're going to consider this the domain and this the range. And remember, the domain essentially makes up how many slots I'm filling up. Well, how many functions are there? If we know there are, I'm not going to draw out all of these, but there are 23 slots to fill with any one of those numbers. Go ahead and finish this off yourself. As we know, any one of these elements in the domain could match with any of these 365 possible options in the range, which means that every slot has 365 different possibilities that could go into here. Therefore, how many total functions exist, right? How many different ways to match exist? 365 to the 23rd power. Well, let's bring back what we learned a minute ago. How many functions are one-to-one? There's going to be fewer than that, but we still set it up in a similar way. Go ahead and take a stab at this yourself as well, and we'll check. So because it's a one-to-one function, once we've used up an element in the range, we can't use it again, right? So it turns into the situation like we had before, 365, but then times 364, all the way down to 343. Now it can be a trick to figure out what that lowest number is. One thing that's helpful, and you probably realize this, is 365 minus 23, but that gives me 342. Well, why do I start at 343? Well, it turns out if I start here up to here, that gives me my full 23 things. But why is it not just direct subtraction? Just a quick thing. If I asked you how many numbers are there from 2 to 5, if all you did was subtract 2 from 5, you'd get 3. But how many numbers are there from 2 to 5? 2, 3, 4, 5. When you do subtraction, it kind of leaves one of those endpoints off. That's the best way to think of it. So anyway, instead of going down to 342, it starts at 343. But notice the difference between our calculation here. This we can repeat something, this we cannot, and that goes with what we call a one-to-one function. Now, this is interesting because this seems like a purely numerical example I'm giving you, doesn't it? Right? This is just a list of numbers, and so is this. But you should think back to a problem we've spent some time studying and looking at, because it should be very related to that. And that has to do with the birthday problem, right? If you remember, in the birthday problem, we were surprised to find out that it only takes about 23 people to have a 50% chance that any two of them will share a birthday. And so you can probably recognize that number as ringing a bell for how many days we have in a year. So this calculation we do here with the one-to-one functions plays an important role in actually tabulating and calculating that probability in the birthday problem. And so it's very related to functions. That's today's lesson. So again, happy math, and we'll see you next time.